several times we have discussed with Anatoly Moiseyevich the beauty of mathematics. And once he said that he believed that people should consider mathematics as a kind of religion, something like that. And we more and more discuss these things, that we should search for something beautiful in mathematics. And these things in intersection, which I will talk about, in an intersection of several fields. And Anatoly Moiseyevich taught that one should not fear to enter new fields of mathematics. He said once that in his experience, the time to enter a new field of mathematics is something about 3 years, he said. 3 years is okay for a new field. And I'm very grateful for him for these new fields that he taught me, because now I can see something beautiful on this intersection of distinct fields. And the thing that I told about is quantization is an example of something very mysterious and interesting that happens on the intersection of several fields. And the ingredients I need will be the braid group, then random walks, then maybe I need Poincaré translation and rotation numbers. Maybe some more things, just like circle, but they are simple and will appear along the talk. So, in fact, our first discussion with Anatoly Moiseyevich was about braid groups and random walks. Once he came to one of my talks about braid groups, and then he said, "Oh, you know very well what the braid group is. I have a plan. Let's study the random walks in this group." At that time, indeed, Vadim Kaymanovich already counted the Poisson first dynamic boundary of random walks and braid groups, but Anatoly Moiseyevich still was interested about distinct phenomena where appear and where we have random walk and braid group. So random walk, we already know the definition. You can just a Markov process with increments. We have a group, for example, the braid group. We have some measure, probability measure in the braid group, and we consider the process of increments chosen with respect to this measure. So in braid group, say we have a braid group. And we have so this is our braid group. So this is the usual geometric presentation when you see these generators as some threads up to isotopy. Oh, and suppose that we have a random walk there. So we say we stand in the trivial element, then with some probability, let it be uniform probability on this set of generators and their inverses. And we imagine this random walk. We stand in the trivial element, then jump into a randomly chosen generator, then multiply by a randomly chosen generator, and so on. And if you say try to see it from the point of view of Cayley graph. Let it be Cayley graph from very far distance, and then this random walk will be just like Brownian motion in the braid group. Yeah? And so this, in fact, this is ingredients from distinct fields of mathematics, but now we have to consider another one ingredient that I know from Viktor Matveyevich Buchstaber and Alexei Glutsuk. At some moment they told us about this quantization effect that they saw on the differential equations over the torus. So suppose we have some differential equations of torus, some multi-parameter equation, which give us each fixing of parameters give us some diffeomorphism of the circle. And for diffeomorphism of the circle and for homeomorphisms of the circle, we have this Poincaré rotation number. It's very famous invariant. You can define rotation and translation. If we have a circle and we have, say, a circle will be like real numbers factor the integers, and then we have the real line as the universal cover of the circle, and then we have in the set of homeomorphism, let be orientation preserving ones of the real line, we have a subset that consists of all homeomorphisms that are lifts of homeomorphisms of the circle. Then if some homomorphisms lies here, then we have for each point there is a limit So if we iterate this automorphism and just divide on the number of iterations, then we will have a limit, and this limit doesn't depend on the choice of x, it depends only on f, and this is the Poincaré translation number for homeomorphisms of the line that are lifts of homeomorphism of the circle. So if we have a graph of such a homeomorphism, then the translation number will be something like that. So it will be almost the translation of the 1 point. Yeah? And they said that if we have some Buchstaber and Leszek Glutsuk, they studied some phenomena on these differential equations and said that for some interesting special multi-parameter equations on the torus, we tried to count the translation number which we obtain when we consider these equations. So if we fix some parameters, if we have an equation and consider some parameters, then for each point we have the image. And with this rotation bound, we can obtain a translation of the real line and count this Poincaré translation number. And the phenomena that they were interested in was that for some equations, the areas in the parameter space when the translation number was an integer were huge. So if we have in the equation several parameters, say t, p, and so on, and they just depict the areas where in this parameter space which give some integer translation number rotations for this circle. And these areas with integer translation number were huge. So we expect that translation number will be something random, say like 1/3, or say something like number e. But they take experiments and saw that the areas where the translation number is integer are huge. And this gives us an idea to make something similar with the braid group. Why? Because on the braid group we have some special invariants, just maps to real numbers that can be defined like via translation numbers. Like I said, you see that the braid group can be considered as the mapping class group of a disk with punctures. Yeah? And on the disk with punctures, we can consider the hyperbolic metric. Yeah, when the punctures are just hyperbolic horns. And if you see take the universal cover space of this object, universal cover space will be something like that. So this is hyperbolic plane, and this one thing is the universal cover of this punctured disk. Yeah? And if you fix some of these lines, which is just universal cover of this boundary of your disk, and then take a factor through a one-time rotation about this boundary component. Then it's take a geodesic, say, and this is some preimage of this geodesic. Then we can take a factor and obtain a hyperbolic crown. This is very complex hyperbolic crown, and any element of the braid group, any automorphism here, can be lifted to this hyperbolic crown, and it gives so we have a crown. The circle here, this circle is just like this one. And a circle there, that circle is a factor of this part of the boundary at infinity. So we have this annulus, and for each braid we can associate a rotation of this annulus, and we can count this translation number for this. So for braid group we have.
Do you expect some decorations in this?
Yeah, compactification. So here we have an absolute, the absolute boundary at infinity. And here in this hyperbolic crown, I have these points from the absolute.
So you have some horocycle.
Yeah, we have the horocycle and so on. But we notice that when I add these points at infinity, this thing is just the compact annulus. And any braid I can see as a homeomorphisms, and lifting this homeomorphism here and then there, I obtain a homeomorphism of this annulus, and just can see it like to compute the translation number by Poincaré, and obtain this map Poincaré translation number from the braid group to reals.
If we take, for instance, B3, so then this is a central extension of SL to Z, yeah? So it's possible to do the same for this simplest case.
Yeah? Yeah. So, but we we're not interested in concrete parameters of this thing. We were interested in this quantization effect. So now we have some invariant on our group, and we try to understand how it behaves on when we have a random walk on our group. And it turns out that we also can see this quantization effect. So in fact, it's a theorem that for braid groups, in fact, the image is rational numbers. And consider now an experiment. We take a braid group, we can count this thing because it's something rational. You can count it exactly. And we just have a random walk, generate at random new and new generators in our braid group, add them and count the translation number for them. And my expectation was that we should have some marks of this quantization effect in that the integers should be more frequent than other numbers. I expected that when I, under the random walk of the braid group, counting the translation numbers of these elements of my path, I expected that I will see something like that say half an element in my path will have integer translation number, because we have something very mysterious in this quantization. But the results of experience were quite very strange. The results were like that. Say, I take an experiment, so I have, say, sigma 3, then randomly choose another one, sigma term minus 1, and so on. And I have elements in the braid group, trivial elements, and this sigma 3, then sigma 3 multiplied with 1 minus 1, and so on and so on. And I have translation number 0, 0, then something like 1 over 5 set, 1 over 4, and so on. Then
translation number for every
braid, yeah. Then 1 set, but then 1 and 1 over 6, say, and something like that. But from some moment, and indeed the number of integers, for example, usually when I come to 1, it over my random walk, that I saw 1 several times before I jumped to something like 1 and 1 over 6. But then from some moment, not very far from the beginning, I said this moment after, say, 100 or 200 steps, in this sequence of translation numbers of points of my random walk, I see only integers. So of course, sometime not integers, but something not integer were very, very rare. And a student, Ledio Deda, made this experiment for me. And first time I saw it, oh, it's just some mistake in your computation, I said. Let's try to check. And we were trying to check, and no mistake, we can't find a mistake. So in fact, and then it turns out that this is a theorem. So if we have any probability measure on the braid group, any probability measure whose support generates the braid group. And we have a random walk with respect to this probability measure. Then for almost every path of this random walk, the proportion of points is in this random walk that have integer Poincaré translation number will tend to 1. So for any probability measure whose support generates our braid group, and for almost every path in our braid group, the proportion of elements with integer translations will go to 1. So from some point, almost all will be integers. So this is a very mysterious thing, but then it turns out that it has a very simple explanation.
Excuse me,
yeah?
How sensitive is that for the braiding relation? So for instance, if you forget about that and take only locally free groups? Or...
Yeah, that the answer is that the braid group is not of importance. We have the same in any group acting on the circle. So in fact, the intuition here proposes something strange. In these experiments, you believe that these translations should be something various, like 1/2, 1/2, and so on. In fact, they are. The principle is that you should, when you try to understand this thing, the main point is that random homomorphism of the circle looks, let's try to do something to show a homomorphism of circle. Say, let's take a circle and some uniform measure on this thing. Say, this is uniform measure, and when we try to take some group acting on this circle and consider random walk in this group, try to check the result, but by seeing what effect our random elements will cause on this measure. Yeah? What will happen if we will try to implement random elements of a group? So say we stand in the trivial element of the group. Then we apply some with our measure on the group. We choose some generator and apply it and say measure deforms into something like that. Yeah? Then again, we choose some random element and multiply by it, and again our measure deforms, say, turns into something like that, and so on. Yeah? So imagine you can see it like a pile of sand over the circular thing, and you just deform this pile of sand. And an intuition says that if we do that a long time, then the result of this shifting a pile of sand will be something like that. But the answer is that, in fact, if we have a group that acts without global fixed points and that acts proximally such that any 2 points can be by this action brought close to each other, this proximality, then the average result will look not like that. The average result of applying a random element of the group will look like huge pile, and then so on. So we have, after applying many times random shifts of this pile of sand, we will obtain result not like that, but like this one. All sand will go to a one huge pile, and in other places we will have a very small amount of sand. Of course, that small amount will have a very complex structure. In this place, say, we have almost nothing, and in this place near this, in 100 times less. And here, more or less, so this not like one and the same number.
But there is a
yeah, but there is
a boundary which.
Yeah, and from the, so this is strange structure, and here also this huge pile, not just something like that. This huge pile has a complex structure, but all this complex structure inside this local huge pile. Just because when you think about the measure as of a sand, of course it's counterintuitive, because distinct part of sands can be arbitrarily close to each other. But if you remember that it's just a measure, then you see it. So we can prove that if a group acts on a circle with no global fixed point and proximally, then generic huge element of this group sends almost all.
Huge in which sense?
Huge in the sense that average that you obtain after, say, 1,000 steps of the random walk.
Okay.
Then this generic element will have such effect on your circle. Almost all circle will go to a small arc. So in this beautiful experiment, well, when we see that the braid group always have generic elements in our path of our random walk, almost always have integer rotation number, what's explanation? That the braid group there is not important, because under our experiment, any group that acts on the circle will, after a 1,000 of steps of our random walk, will send almost all of our circle in a small arc. And usually we have just a fixed point. So generic element of the group, of our group acting on the circle, generic element will have a fixed point. And then, of course, the translation number will be an integer. So at first glance, we think that we have some mistake or something paradoxical, but from the point of view of random walks, these have a very nice explanation. And I believe this is a beautiful counterintuitive phenomena that somehow related to many other things that use the name quantization.
Can you just say again what was the condition, the proximality condition? What does it say?
Proximality condition is that for any 2 points of our circle, we have a sequence in our group such that distance tends to 0 as I tends to infinity. So we can make any 2 points close to each other, arbitrarily close to each other. In fact,
so do I understand correctly that this condition implies actually that the group has non-trivial Poisson boundary?
Yeah. But in fact, for groups that act not proximally, it's only very special groups. So every time you have a group acting on the circle, you have a minimal subspace of the circle that's invariant. So usually it's just the Cantor subset. And to be non-proximal, we should be non-proximal on this subset. And if and gluing the ends of these intervals from this Cantor subset, we obtain a circle again. So if a group acts non-proximally on the circle, then it acts non-proximally on some subcircle. And if it acts non-proximally on this subcircle glued from the Cantor set, then either it acts by isometries or it covers some proximal action, so all action commutes with some shift of the circle. So these are very rare cases. So usual action is proximal. Just we exclude something degenerate. In other sense, when I'm saying that if a group acts with no global fixed points and proximally, I'm just saying if a group acts degenerately. If an action of a group is degenerate, then each time we have this mysterious behavior. But it is mysterious only because intuition don't tell us immediately what's the behavior of this measure of this generic element. But when we go inside the theory of random walk, we know that generic element of group acting on this circle is really strange, but it's generic elements all like this. They send all your circle in a small, small arc. So, but why can we see this? Because Anatoly Moisеевич told us, go and read many papers about random walks. But now we know these effects. So that's all. This a little mysterious, beautiful thing. Very strange phenomenon. Thank you.
These questions. Comments? Yeah.
Thank you. Very interesting talk. Say a little bit, is it intuitive? What you say that, so you say that if we have a generic element, then there is one point which...
This is contra-intuitive when you read 10 papers about random walks, and this is completely intuitive when you read, say, 100 papers about random walk.
I think we should explain why it is intuitive.
No, but I can prove that. And when you saw the proof, you yeah, really, of course, it's like...
How long is the proof?
It's not very long, it's about 3 or 4 pages.
Other questions? No, just a maybe naive question. It's what I wanted to ask you during your talk. Do you have a size of this small band, some kind of boundary where no go for this?
The size is for any epsilon. If I have a group acting on the circle degenerately with a given measure, probability measure on this group, then for any epsilon, I can choose a large n that depends on this mu and epsilon, such that after such number of steps, with probability 1 minus epsilon, all the measure will be on the arc on length epsilon, and this thing will be less than epsilon.
Okay, I understand.
So that was almost my question. How, for instance, suppose that you make a restart. So you start your experiment, so then you get these bursts, you stop. So then you start again. So you get it always in the same place, or
no, it shifts. So the place where it's like this boundary is this circle is a boundary of our work because this spike shifts here. So the place when it shifts depends on, but the phenomenon that we have it is usually when you have with large probability, when it forms first time, then it survives for infinity. But of course it changes. So some parts will go there, some parts of our sand, of our measure, will go inside, and some can go outside. But the shape survives.
Other questions? If not, let's thank Andrey again.
Okay.